The main focus of this video is the first law of thermodynamics. To build a solid understanding of this fundamental principle, I will cover the following topics: systems and surroundings, internal energy, the first law of thermodynamics, and the applications of the first law through a couple of worked example problems. A system is any object or group of objects that we choose to study and analyze. Examples of systems include a gas contained in a cylinder, water in a beaker, or an engine. Everything in the universe outside the system is referred to as the surroundings. The internal energy of a system is the total energy associated with all the molecules or atoms that make up the system. Thus, internal energy is related to the microscopic energies of the molecules or atoms. It includes the translational kinetic energy of the molecules, the rotational kinetic energy of the molecules, the vibrational kinetic energy of the molecules, the potential energy associated with intermolecular forces. Therefore, internal energy is the sum of all these microscopic forms of energy within the system. It is important to note that internal energy does not include the energy of the system as a whole. For example, if the entire system is raised to a certain height, it acquires gravitational potential energy. This energy is not part of the internal energy. If the system as a whole is moving, it possesses macroscopic kinetic energy. This kinetic energy is also not part of the internal energy. To derive the first law of thermodynamics, let the initial internal energy of the system be U1. Now suppose the system absorbs an amount of heat, Q. Since heat is a form of energy, adding heat to the system increases its internal energy. Therefore, after absorbing heat, the internal energy becomes U1 plus Q. A system can also do work on its surroundings, or work can be done on the system. Let W be the work done by the system on the surroundings. When a system does work, it transfers energy to the surroundings and therefore loses energy. Hence, the work done by the system must be subtracted from its internal energy. This is the final internal energy of the system, U2. From this equation, U2 minus U1 is equal to Q minus W. U2 minus U1 is nothing but the change in internal energy of the system. So delta U is equal to Q minus W. This equation is known as the first law of thermodynamics. It states that the change in the internal energy of a system is equal to the heat added to the system minus the work done by the system on its surroundings. The first law of thermodynamics is a statement of the conservation of energy that accounts for energy transfer in the form of heat and work. Next, we will see how to apply this law to different thermodynamic processes. In the first law of thermodynamics, Q represents the heat absorbed by the system. If the system releases heat to the surroundings instead of absorbing it, energy leaves the system. In that case, Q is negative. Similarly, W represents the work done by the system on its surroundings. If work is done on the system instead of by the system, energy is transferred to the system. In that case, W is negative because negative of negative is positive. Now let us solve a couple of problems to see how the first law of thermodynamics is applied. In this problem, the system is a gas in a piston cylinder. The system absorbs 450 joule of heat from its surroundings. Since heat is absorbed by the system, Q is positive 450 joule. During the process, the gas expands and does 175 joule of work on the surroundings. Since the work is done by the system, the work is positive 175 joule. Now use the first law of thermodynamics to determine the change in the internal energy of the gas. Substitute the values of Q and W is equal to 450 joule minus 175 joule. is equal to 275 joule. Therefore, the change in the internal energy of the system is 275 joule. In this problem, the system is again a gas. The gas is compressed by an external force, and 320 joule of work is done on the gas. Since the work is done on the system, the work is negative. So W is equal to negative 320 joule. At the same time, the gas releases 140 joule of heat to the surroundings. Since heat leaves the system, it is negative. So Q is equal to negative 140 joule. Use the first law of thermodynamics to find the change in internal energy. Substitute the values of Q and W. Is equal to negative 140 joule minus negative 320 joule. Is equal to 180 joule. Thus, the change in the internal energy of the gas is 180 joule.